Hey everybody, today we're going to talk about the kinetic molecular theory and behaviors of gases. Now in previous units we've talked about some brief and basic properties of gases, so we're going to kind of recap that and review it a little bit more, and we're going to talk about the kinetic molecular theory, and then we'll get into gas laws ultimately. So the kinetic theory basically says that tiny particles in all forms of matter are always moving. They are always in constant motion. So you have, let's say, an object here, a container that's filled with gases. Well, all of these gas particles, whether they be individual elements or molecules, they are continuously moving. And since they are continuously moving, they are continuously hitting the edge of the container. They're continuously hitting each other, but nonetheless, they are always in constant motion. So the kinetic theory has five basic postulates or principles to base off of. The first one says gases are composed of small, separate particles called molecules. These could also be individual elements as well. So it could be something like hydrogen gas, chlorine gas, and so forth. These gas molecules are always in constant motion, like we mentioned a second ago. They're always in constant motion. They're continuously moving. In some cases, they'll move faster than others. But nonetheless, they are in constant motion. So if something is in motion, then we would say that that object has kinetic energy. So kinetic energy is the energy of motion, which is where we get our title, kinetic molecular theory, because these molecules are always moving. All collisions between particles are perfectly elastic. So what does that mean? Elastic means that two objects are going to hit each other and they're going to bounce apart. So in other words, if I've got a molecule here that's moving this direction and a molecule or an element here moving this direction, when they hit each other, let's say this is the moment that they hit each other, after they hit each other they are going to bounce apart. So they're going to go their own separate ways in opposite directions or different directions. So that's what elastic means. They're going to hit each other and they're going to separate. In other words, they're not going to stick together. The fourth postulate or assumption says that molecules of gas display no attraction or repulsion towards each other. So we're assuming here to make this theory, I guess the calculations a little bit easier. We're assuming that there are no forces of attraction and there are no forces causing them to repel from each other. They just hit each other and bounce off. And the fifth one here says the average kinetic energy of the molecules is directly proportional to the Kelvin temperature of that gas. So what does that mean? Well, as temperature increases, then that means that the movement, the kinetic energy of those molecules also increase. So the warmer or the hotter the gas is, the faster these molecules of that gas move. They are directly proportional. That's what directly proportional means. They're going to do the same. So if the temperature goes up, then the speed or the rate at which these molecules move also increases. Okay, so be familiar with these five. We'll revisit these as we go along, looking at behaviors of gases and then also into laws of gases. So these five are the five postulates, the five assumptions within our kinetic molecular theory. So there's an ideal gas and a real gas. So an ideal gas is a gas that conforms to everything that we want it to conform to. It's basically a perfect gas. And so this is a theoretical gas because perfect gases don't exist. So the gases that we experience on our day-to-day basis are considered real gases. And particles in a real gas have their own volume. They take up the space of whatever container they're in. They do attract. There is some attraction to one another. Gas behavior is most ideal at low pressures, at high temperatures, and in nonpolar atoms or molecules. So what are some characteristics of gases? Well, we know that gases expand to fill any container that they're in. So if I stand on one side of the room and I spray a spritz of perfume, if you're sitting on the other side of the room, you might not smell it right away, but over time, that gas is going to diffuse, and it's going to eventually spread out throughout the rest of the room. So eventually, the person that's sitting on the other side of the room will be able to smell it. And that is known as diffusion. Let me write that. Oops. Gases are fluids as well. So what does that mean? Well, a fluid pertains to anything that can flow. So liquids also flow, the molecules flow around each other. In gases, those molecules or elements also flow around each other, considering them to be fluid. Gases have very low densities. Okay, they're the least dense of solids and liquids and gases. So solids are the most dense. And gases are the least dense. Gases can be compressed. Gases are compressible. So I compress these gases together into a smaller size container. So if I've got, let's say, a container here that's got, for demonstration purposes, let's say it's got 5 molecules of gas in this container. If I were to take that gas and let's say I compressed it, so I pushed down on that gas, so now I've got the same 5 molecules of gas, but now they're in less space. Okay, so here they had more volume. Over here they had less volume. And eventually you could compress a gas to form a liquid because you're forcing those molecules to become so close together to one another. Number 5, gases undergo diffusion and effusion through random motion. We kind of mentioned that up above. Some factors that affect behaviors of gases. We've got pressure. Pressure certainly affects the behavior of a gas. Volume affects the the behavior. Temperature and the number of moles, or the amount. So the amount here, and that's going to be expressed with the letter N. I'll talk about that here in a second. So pressure. Pressure is the force per given area of gas as a result of the forces particles hit the walls of a container. So these particles, let's say if they're in a container, if they're moving in that container, they are constantly bouncing and hitting those walls. So the force at which they hit these walls is related to the pressure in which they're exerting on that container. So normally we'll measure pressure, which is expressed as a capital P. We'll measure it in kilopascals, which is often abbreviated as kPa. Volume. Volume is the space that is taken up by the gas, referring to the size of the container. We usually measure it in liters. However, we can also measure in cubic centimeters. We can also measure it in cubic meters, but the liter is pretty common. Temperature. Temperature is symbolized with a capital T. Temperature is measured in kelvins. Now, a lot of times you would refer to temperature as degrees Celsius or degrees Fahrenheit, but when we are dealing with temperature of gases, we are always going to measure in kelvins. Always going to measure in degrees Kelvin. We'll talk about what that means here in a moment. The last factor that affects the behavior of a gas is the number of moles, which is referring to the amount. And we refer to the amount as a symbol N. So a lot of times if you can convert to the number of moles, that makes stoichiometry so much easier, which we've practiced here in the past. So gas pressure is the pressure which is equal to the force over area, and that determines how many atmospheres is created when these gas particles collide with their container. Atmospheric pressure is the pressure on Earth's atmosphere due to the weight of the gas that is pressing down on us. So you've noticed that maybe if you've gone on a road trip or you've hiked up a mountain, you might notice that your ears pop. If you go down the hill or the mountain, you notice that your ears pop. If you've gone on a plane, you notice that the ears pop, because as you ascend and descend with your regarding elevation, the amount of air pressure that's pushing down on you changes. The same concept is true if you've ever gone swimming or diving. If you swim down to the deep end of 10 feet, 12 feet pool, you'll notice that you start to feel a lot of pressure because you're feeling all that water pressing down on your body. And it's less noticeable when you're at the surface because you have less water pushing down your body. And a barometer is just simply an instrument that's used to measure that atmospheric pressure. So some units that you'll need to be familiar with is the kilopascal, kPa, the atmosphere, atm, millimeters of mercury, torr for torricali, and psi. So what do all these stand for? So kPa stands for kilopascals, shortened abbreviated form for kilopascal. ATM refers to atmosphere. mmHg is short for millimeters of mercury. Hg is a symbol for mercury. Torr is short for torricelli. And psi stands for pounds per square inch. Now, what's unique about these is that 101.3 kilopascals is equal to 1 atmosphere, which is equal to 760 torr, which is equal to 760 millimeters of mercury. So eventually, we're going to be looking at these conversion factors. We're going to be using these conversion factors, and you'll have to refer to these. You'll have to remember that 101.3 kilopascals is equal to 1 atmosphere, which is equal to 760 torr, which is equal to 760 millimeters of mercury. Now, no, you will not have to memorize this. You will have this available to you, but just know where to refer to this and how they're related. So, standard temperature and pressure, STP. So, standard temperature is 0 degrees Celsius, which is 273 degrees Kelvin, which I'm going to show you what the Kelvin scale looks like here momentarily. Standard pressure is 1 atmosphere, which is 101.325 kilopascals. So, you'll need to be aware that this is your standard temp. And this is your standard pressure. And remember that 1 atmosphere has an equivalency to a certain amount of torr, kilopascals, pounds per square inch, and so forth. So here's what we're looking at in regards to temperature. So normally we here in the United States, we measure temperature in Fahrenheit. So freezing occurs at 32 degrees Fahrenheit. So this is freezing. So 32 degrees Fahrenheit, water freezes. which is 0 degrees Celsius, and 273 degrees Kelvin. Water boils, this is the boiling point of water, at 212 degrees Fahrenheit, which is equivalent to 100 degrees Celsius, which is equivalent to 373 degrees Kelvin. 0 Kelvin is equal to minus 273 degrees Celsius and minus 459 degrees Fahrenheit. So anytime that we are in the negative temperatures here in the States, we know it's cold. Anything below 32 degrees Fahrenheit is really cold. Can you imagine being this cold? Negative 459 degrees Fahrenheit. That's really, really cold. And that is equivalent to 0 degrees Kelvin. So some conversion factors that you may need to be familiar with. What if you're given degrees Fahrenheit and you want to convert that to degrees Celsius? Well, you would plug in your temperature, whatever temperature you have of degrees Fahrenheit, subtract 32 and multiply it by 5/9, and you get your temperature in Celsius. Since we're going to be using Kelvin quite a bit, if you're given temperature in Celsius, all you have to do is add 273 degrees to it. If you are given Kelvin and you need to convert it to degrees Celsius, then it is degrees Celsius equals your temperature in kelvins minus 273. So converting Celsius to Kelvin or Kelvin to Celsius is an easy one. It's simply the addition or subtraction of 273. So we're going to measure gas temperatures in Kelvin, so we'll have to be familiar with this conversion. Converting Celsius to Fahrenheit, we're not going to be using that much in this unit, but here's your equation, your conversion equation if needed. So before we move on, I want to do a quick example with you guys. Let me zoom out just a little bit. Okay, so let's say I want to know how many kelvins is 45 degrees Celsius. So how many kelvins is 45 degrees Celsius? Well, I'm going to use my conversion here. And it says that kelvins is equal to your temperature in Celsius plus 273. So kelvins is what I want to know. This is my temperature in Celsius. So K equals degrees Celsius plus 273. So kelvins are unknown. My temperature in Celsius was 45 degrees. And I add 273 to that. And 45 plus 273 is equal to 318 kelvins. Okay. What about how many kelvins is negative 25 degrees? Okay, so again, I want to solve for kelvins. I want to know how many kelvins that is. And I'm given my temperature in Celsius. So kelvins equals my temperature in Celsius plus 273. So my temperature is negative 25, and I'm going to add 273 to that. So negative 25 plus 273 gives me 248 kelvins. So we're going to talk briefly about some gas laws. We're going to get into gas laws as the unit progresses. But what gas laws are, they're just simply mathematical formulas that explain how a gas behaves based off of certain factors like pressure, volume, the number of moles, which is the amount, or temperature. So based off of these four factors, we have a series of gas laws, equations that we're going to be using that will help us determine how much pressure, volume, an amount, or the temperature of a certain gas. So So one of the first laws we're going to look at here as an introduction to gas laws is called Dalton's law. It's Dalton's law of partial pressures. So what that says is that the total pressure of a gas mixture is equal to the sum of the partial pressures of each gas. In other words, the total pressure is equal to the sum of the individual pressures of each gas. For example, if I've got oxygen in a container here, and I've got nitrogen in a container here, I want to determine, or I can determine, what the total pressure of those two gases combined would be. So PT is total pressure. So PT is total pressure. So oxygen plus nitrogen, this would be my total pressure. P1 is a partial pressure of the first gas. So let's say that oxygen is my first gas. That's P1. P2 is my partial pressure. It's the individual pressure of my second gas. So I'll say nitrogen is P2. P3, I can keep going. Depending on how many gases you have, that will determine how many times you keep adding the individual pressures of each gas. So I've only got 2 here. I've only got oxygen and nitrogen, so I'm stopping at 2. So the total pressure is equal to the sum of these, which means you're adding them. So it's as simple as taking the pressure of oxygen plus the pressure of nitrogen and combining them to get the total pressure. So what you see down here at the bottom is that oxygen has a pressure of 159. Plus nitrogen has a pressure of 593 equals oxygen plus nitrogen is 752. So 159 plus 593 equals 752. It's as simple as that. You just add up the individual pressures to find the total pressure. That's the law. So here's a quick example. It says calculate the total pressure in a flask that contains hydrogen gas at 546 torr, oxygen gas at 736 torr, and water vapor at 54 torr. So remember these units, torr, and torr. Torr measures pressure. Okay, so what's given you is units of pressure. So I have hydrogen gas that has a pressure of 546. So we'll say hydrogen has 546 torr. Oxygen gas is 736. And water vapor is 54 torr. So I want to calculate the total pressure, which means I want to solve for PT. So how do we find PT? Well, we know that PT is equal to the sum of the individual pressures. So I've got 3 different gases. So I've got the pressure of one gas, plus the pressure of my second gas, plus the pressure of my third gas. And I can label these. I'll say this is P1, this is P2, this is my third gas. Okay, there's P1, 2, and 3. So for P1, the pressure of hydrogen, I had 546. P2, the pressure of oxygen gas, I had 736. And for P2, the pressure of water vapor, I had 54. So with those individual pressures, all I have to do is add them up to get a total pressure. So after adding them all together, I should get a sum of 1,336. 1,336 torr is my total pressure of hydrogen, oxygen, and water vapor. In my second example here, it says a pressurized tank contains a mixture of oxygen gas at 325 psi and nitrogen gas at 1,256 psi. If the tank also contains helium gas, what is the partial pressure of helium if the total pressure is 2,457? Okay, so it's telling me that this tank contains different gases. I've got oxygen gas at 325, so I'm going to write oxygen gas at 325. I've got nitrogen gas at 1,256. It says the tank also contains helium gas. What is the partial pressure of helium if the total pressure is 2,457? So it doesn't tell me the pressure of helium. That's what I want to find. It says the total pressure is 2,457. So we'll call this P1, we'll call this P2, call that P3, which is unknown, and then it gives me my total pressure. PT of 2,457 psi. All right, so Dalton's law of partial pressure says that the total pressure is equal to the sum of the individual pressures. So I've got three different gases. So I'll say P1, P2, P3, and now I fill in what I know. The total pressure was given to me as 2,457 psi. The pressure of oxygen, which I labeled as P1, has a pressure of 325. The second gas, which is nitrogen, I'll label it P2, has a pressure of 1,256 psi. And helium, my third gas, is unknown. So I'm just going to write it as P3. You can write it as an X. Either way, it's your unknown variable. So it just comes down to adding and subtracting. So I can combine like terms. I can combine these two if I wanted to. So 325 plus 1256 equals 1581. So 2,457 equals 1,581 plus P3. And now to get P3 by itself, I'm going to subtract 1,581 from both sides. So these cancel out. And I've got 2,457 minus 1,581. And I should get 876 psi is the value of helium, which is P3. And if you want to check your answers, you can plug in 876 into this equation and see if 876 plus 1256 plus 325 equals 2457. If it does, you're correct. If it's not, then recheck your math.